Hello and welcome to the Daily Space for today, Thursday, September 17th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. With today's news, I feel like the cycle of planetary discoveries has finally come back full circle. Back in 1992, Alexander Wolfskin and Dale Frail they announced the discovery of a multiplanetary system around pulsar PSR 1257 plus 12. In this case, by planet, they meant lumps of rock roughly 4 Earth masses in size and orbiting at distances slightly larger than Mercury's orbit around the Sun. At least we assumed they were lumps of rock since these objects would have had to survive a blast from a supernova explosion that formed the pulsar. These were the first exoplanets discovered, and they'd be followed in short order by the discovery of hot Jupiters in 1995. While most of our attention on exoplanets has since then focused on planets around regular stars, astronomers have continued to find worlds around dead stars, including the 2000 discovery of a planet orbiting a neutron star white dwarf binary system, and many subsequent discoveries of rocky, assumed to be wreckage around white dwarfs and heavier neutron stars. During the roughly soon-to-be 30 years of exoplanet exploration, many have wondered if white dwarfs, which represent the future evolution of our sun, are capable of having regular gas giants orbiting them. Fundamentally, we want to know when our sun dies, what worlds will have a chance of sticking around. We know the sun will expand out into a red giant and eat a few worlds in the process. We know it will undergo significant mass loss, especially as it forms a planetary nebula and sheds its outer atmosphere. And that could alter planets in myriad of ways. What exactly will happen to our solar system? We just don't know. Well, we now know at least that gas giants can be found around white dwarf stars. In a new paper published in Nature, a team that includes Andrew Vandenberg as first author finds that one gas giant orbits a white dwarf. Using data from TESS, Spitzer, Gemini North, and the Hobby-Eberly telescope down in Texas, they find that the planet is no larger than 13.8 Jupiter masses, and it orbits every 34 hours. This is an odd-looking pair, with the star being about 4 times the radius of the Earth and the planet being order of 10 Earth radii. What struck me about this discovery is the gas giant appears to have a temperature not too different from Earth's temperature, about 17 degrees Celsius. This makes me imagine an Endor-like moon evolving in this new configuration. This doesn't mean such a thing exists. It just is cool to think about, cool to imagine. And let me make it clear. This is a new configuration. The planet had to migrate to where it is today. It's not entirely clear how planets like this migrate into new and stable orbits so close to their stars, but we know they can. In all likelihood, this system started with the gas giant much further out, and somehow it got knocked into an elliptical orbit through interactions with other planets. And tidal effects that included stretching this planet out, they were able to circularize this orbit into what we see today. However this happened, this means we get to imagine cool new futures for stellar remnants. Let the science fiction writing begin. Looking at the other side of stellar evolution, in a new article in the Astrophysical Journal, Ryan Liu and company share new observations of a massive young star called a Wolf-Rayet star that is in orbit around another massive star. This system is acting like a super hot sprinkler where instead of water, it is jetting out spirals of dust. Wolf-Rayet stars are known for having hot jets driven by magnetic fields. As these two stars in this system orbit roughly every 20 years, the source of the jets, that Wolf-Rayet star, moves like a spinning sprinkler head and changes the source of the jet over time. This is leading to an amazing spiral that we have an odd side view perspective on. The random alignment of this system has the two stars orbiting almost perpendicular to the plane of the sky. So the spiral we see is like the water flying out of that imaginary sprinkler head as viewed across your lawn. This system isn't just a case of really cool geometry. It is also a case of weird chemistry and physics leading to a hot system producing dust, something usually found in cooler situations. According to co-author Anthony Moffat, who uses somewhat strong language, when the two stars' winds collide, all hell breaks loose, including the release of copious shocked gas X-rays, but also the, at first blush, surprising creation of copious amounts of carbon-based aerosol dust particles in those binaries in which, I'm so sorry, my teleprompter just temporarily lost its mind. Carbon-based aerosol dust particles in those binaries in which one of the stars has evolved to helium burning, which produces 40% carbon in their winds. This system has it all: geometry, chemistry, physics. Those of you who have been enjoying our daily space for a while may have noticed that our ideas about where dust and various elements come from have been evolving in recent years. One of the biggest changes in the realization is the realization that neutron star collisions contribute gold. But new work appearing in the Astrophysical Journal with lead author Andrew Masterson shows that merging neutron stars on their own are not enough to get the job done. To be fair, every element can be produced in more than one way by nature. In their paper, they try and lay out all the ways the elements from carbon to uranium come to be through new models. And in the process, they point out, well, gold, we still have some work to do. According to co-author Kobayashi, for example, we built this new model to explain all elements at once and found enough silver, but not enough gold. Well, silver is overproduced, but gold is underproduced in the model compared with observations. This means that we might need to identify a new type of stellar explosion or nuclear reaction. We're getting there with understanding the origins of elements. We're just not all the way there, not yet. As a final note, before we get to today's interview, I'd like to point out that a consortium of solar scientists has declared the next sunspot cycle should be similar to the one we just experienced. Nothing too exciting and nothing too dangerous, but with just enough solar activity, just enough flares and coronal mass ejections to make some awesome aurora and to keep the sky interesting. It's expected that the next solar maximum should occur in 2025. So start planning your aurora watching trips today. So that concludes today's news, but does not conclude this episode. In just a moment, I am going to be joined by Professor Sara Seager of the Massachusetts Institute of Technology. She is part of the amazing team that announced the discovery of phosphine in the environment of Venus's atmosphere earlier this week. So I'm going to put up the rocket's hold video and be back in just a moment. So don't go anywhere. The science continues. Hello, everyone, and welcome back. Joining me is Professor Sara Silva. Sorry, I'm just going to mispronounce everything right now.
Seager, Sara Seager.
Yes, I knew that. I just am having a mispronounce things day. So sorry, Sara. Um, you must be having one heck of a week this week.
Yes. Well, the response has been completely overwhelming. I mean, I expected interest, but not nearly at this level. It's been amazing. And some journalists, they come back now again for like a second, more weekend like in-depth interview or report. So it's just been going on and on and on.
And this has been a slow roll. There was a paper that came out back this summer that you and several of your collaborators postulated how life could exist in the rising and falling apart water droplets, or moisture droplets rather, in the atmosphere of Venus. And there were a number of public level but still sciencey journal, so Discover articles, astronomy.com articles. How long have you been working on papers side by side, looking at the theory and the observations and trying to figure out how are all of these going to hit the journals? This must be a multi-year process.
Yes. Well, the team lead, Professor Jane Greaves, had been working on this for 5 or 6 years, actually. I want to say 4 or 5 years. And her team and my MIT team connected about 2 years ago. So I've been working on this for about 2 years. But the paper that came out this summer that you're referring to it was really because we knew this phosphine result was going to come out eventually. And the team had pushed me to try to explain how could life in Venus, if there is life in the clouds, how could it stay up there indefinitely without being rained out? And we hadn't planned anything, but there was an MIT journalist student or a science writing student who really wanted to do an article on it. And I said, sure. And she did such a great job that it really took on a life of its own. So we hadn't planned it. We hadn't intended it to be like a prelude. It just sort of was in the natural course of when the paper got finished and reviewed and published. And then, yeah.
And at that point, when that paper was coming out and you were starting to see the popular articles in, like I said, Discover, astronomy.com, about this potential life cycle, you knew already at that point about the phosphine, didn't you?
I did, because the work on phosphine was a motivation for trying to plug some holes in the speculations about life in the atmosphere. So it's definitely related.
And how hard was it to talk to all of these people about the theory side, knowing how soon the observations were coming?
Well, we're under strict self-imposed secrecy.
Yes.
And the team lead especially emphasized we must not talk. So I didn't have any problem. I mean, it may seem a bit dishonest, but like the loyalty to the team like really is the most important thing.
Yeah, I totally understand that. It's the I know I have to. I know I have to. We yes. Doing science can be one of those things where you spend a great deal of time knowing things and not being able to answer questions. And it sounds like you don't struggle with this the same way I do. Now, with all of this work, in trying to understand how life could exist in the atmosphere of Venus, Venus is a weird world in terms of its day is longer than its year, it's flipped upside down, it's had something catastrophic happen to it in the last billion years, launching this runaway greenhouse effect. The research that I've seen so far, and I'm still working to absorb all the literature. Uh, looks very simply at you have this moisture cycle in the atmosphere. Now, are you expecting that as we're able to study this in more detail, there'll be differences from the day night? What differences have you seen with latitude? Or is this all just too new at this point to really look at those details?
Well, we only had 3 hours on Alma, which
Yeah.
is still enough. So we only can say what we reported on in the paper right now. That's all we really know, that we see it phosphine at a very generously defined mid-latitude from 15 to 16 degrees, 15 to 60 degrees latitude. We don't see phosphine at the poles. And our data at the equator wasn't really good enough. So I think your question I can only answer by saying hopefully in the future we can get more information.
And what do you expect might be differences if you see them? How does this moisture cycle, for instance, do you know how does it vary with
No,
no idea?
no.
That this is why we do science. It's to try and figure out all these things that we just don't know yet. Now, you are lucky enough to be working with the Breakthrough Institute, and folks are looking at what kinds of spacecraft are possible. And this is quite suddenly opening all sorts of new, well, money is getting thrown at this science. What are the things that you are most excited that this is going to give you the opportunity to do?
Well, I'm most excited that it will reinvigorate space missions to Venus. Here in the US, NASA has sponsored 2
Yeah.
Discovery class mission phase A studies. So there are 2 missions that are in the process of being studied. They're in a competition phase right now. And it's 2 out of 4. There's 4 missions being studied, 2 are Venus missions. So hopefully this will push if it's a matter of popularity, that hopefully one of those might get selected. Russia, India are both planning to send missions to Venus. And as you mentioned, I have my own study sponsored by the Breakthrough Initiative. So hopefully something good will come of this.
And one of the interesting things to get into inside baseball about the timing of this is the planetary science community and the astronomy community both do decadal surveys in which we turn to our entire community and we say, what should be the things that we focus on trying to answer in the next 10 years. And right now is when the planetary science community is going through what's called the white paper process, where people are putting together papers, signing them, and saying, here's what I want to see. Are you seeing that the timing of this is perhaps going to have the ability to influence the decadal survey in ways that it wouldn't have otherwise?
Not sure about that. I'm not sure how the decadal will choose to take this.
Okay. It's early days. White papers are still going in. Now, one of the interesting struggles with doing this research is you have spent much of your career looking at and considering exoplanets, planets orbiting around other stars, and trying to identify biomarkers. Can you tell our audience a little bit about what that process has been and what a biomarker like phosphine means and why it's so important to discover?
Sure. Well, we call it a biosignature gas, a gas that is produced by life that can accumulate in an atmosphere to detectable levels, remotely detectable levels. And Earth, our best biosignature gas here is oxygen. You know, we all need oxygen to breathe. And it's pretty incredible that without plants and photosynthetic bacteria, we would have virtually no oxygen. Yet we have 20% oxygen by volume. So like if you pause to think about that for a moment, life completely re-engineered our atmosphere. I mean, that is just so crazy. So we're hoping that on exoplanets, planets far away, life there also was able to not just produce byproduct gases, but also to re-engineer the atmosphere by producing a ginormous amount of one gas or another. And there's some growing number of astronomers working on this. Like if you ask, especially like it's correlated with age, the younger, the more people want to be finding signs of biosignature gases as their career goal. So it's a growing field. Right now, we can't really detect that. We don't have the ability really to study small rocky planet atmospheres thoroughly yet.
And this is a very new field. It started to receive major funding in the mid 90s and late 90s from NASA with the establishment of the Astrobio Institute. We saw popular level books from folks like Peter Ward, who wrote Life as We May Not Know It. And the idea is that we are looking for chemistry that doesn't have a way of existing through just standard old processes of you leave the
Not always,
chemicals alone.
like
Okay.
not always, because another really touted biosignature gas is methane.
Yes.
People love methane as a biosignature gas, but we also have methane produced without life here. So it's kind of not, it's very hard to find a gas. I mean, phosphine is one of them that isn't isn't usually produced by geochemical or geophysical processes on a terrestrial-like planet that's oxidized. So yeah.
So here we're looking at a situation where with phosphine, we can't identify those geochemical processes. We can't identify photochemical processes taking place with the interaction between sunlight and the atmosphere that would drive its creation. Is that an accurate statement?
We can't. It doesn't mean there isn't one, but we haven't been able to think of one yet.
And so if this was, and here I'm going to get into asking you to speculate, I apologize. If this were a planet 80 light years away that we were someday in the future using a telescope we don't have yet to detect phosphine in its distant atmosphere, would it be easier to say we found a thing that looks like life than it is when the world's right there next to us?
Well, it depends how much you find. I think that's the crux of it. So on Venus, we found about 20 parts per billion of phosphine, which doesn't sound like a lot. That means if you have a volume of air and you counted up a billion particles, 20 of those would be phosphine molecules. But it depends how much. Like if you have so much that it's really not explainable by other processes, then the case is more favorable for that kind of inference.
So when we find phosphine at Venus, we have to, as scientists, hedge our bets. We have to say, I don't know of another way to explain this, but the universe keeps proving to be more creative than we are in the things it comes up with. And so here we have this amazing result where I think a lot of us want to say it's alien microbes, but we can't scream that from the rooftops because...
Well, we don't have enough evidence for that.
Right.
So yeah, can't really say that.
What evidence do we need beyond simply scooping some up and analyzing it under a orbiting or balloon carried microscope? Is there other evidence that could get us to that
Not
point?
really. Really, my personal opinion is we need to go there and we need to sample the atmosphere directly. But even a microscope may not give us a clear-cut answer. There's a lot of confounding particles, aerosols, droplets, and other things. So we really have to do our homework in terms of what would really be a unique signature.
Ideally, you want to see the mitosis, the breaking, the multiplying of the cells underneath a microscope, and that would be amazing to see that desiccation cycle of going from spores to coming back with the addition of moisture. What kinds of experiments, if the sky was the limit, would you want to see?
Well, I'd love to see, if the sky was the limit, a series of missions focused nimble, flexible missions to Venus. And then each one could build on what the prior one found. I'd like to see a balloon, an aerial platform, a variable altitude one, so it could float up and down in that whole temperate cloud region. I'd like to see us being able to look for complex molecules that could be associated with life, and a microscope, and try our best to see if we could even see any life.
And so here we're looking at going to between 45 kilometers, 50 kilometers above the surface in that magical, roughly one Earth atmosphere part. How much further down is that haze layer where the spores might be?
Well, this habitable zone region, so to speak, is about, say, between 50 to 60 kilometers.
Okay.
You could say 48 to 60.
Okay.
And this haze layer is between about 35 to 48 kilometers above the surface.
So that's not a huge variation. What challenges do we still need to figure out other than funding for these kinds of emission?
Well, we need funding, but we're still struggling to, we need some basic measurements as inputs. Like, we'd like to know what are all the chemical species at each altitude of the planet atmosphere, including the surface. We don't have that. The atmospheric mixing vertically and, in 3 dimensions, we don't have a great handle on that either. So it would be great to get more measurements. And I think just people power, working on models, working on chemistry would really help us move forward.
So here we're looking at needing to do potentially mass spectrometry. How much of this requires sampling versus imaging? How much can be done from being above the clouds or even at Earth versus needing to be within the clouds?
Well, we'll do what we can. And of course, it's much cheaper and easier to observe from Earth.
And from Earth, one of the more frustrating parts is Venus at its average size is about 10 arc seconds across. That's 10 widths of a human hair held out at arm's length. And we're generally happy if we can get 1 arc second resolution out of most telescopes. So we're looking at something that might appear 9 pixels across in your typical kind of a setup. What resolutions do you need to start getting those answers that you're more interested in?
Well, I think the team wants to understand the distribution of phosphine across the planet. So I think that's a really good resolution. You have to understand that if you can go into the atmosphere, you can amplify your signal because you can collect gas in a IR spectrometer. And instead of just getting the light from the planet, you can send a laser like light back and forth, back and forth, back and forth until, you can do that so many times. So you can get a path length that's extremely long.
So,
and you're set to much smaller amounts.
So what you're talking about here is the way we do spectroscopy at the Earth is we're relying on sunlight coming off the atmosphere, and you can only get so far with that.
Not just sunlight, sunlight's and reflected light. We also are relying on processed radiation, thermally processed radiation. That is like an emission instead of reflection, but It is all sourced from sunlight originally.
And with that laser light, it allows you to amplify what you're looking at, take the light source with you, essentially.
Right.
Now, have we done that kind of an experiment anywhere? Where have we seen these types of equipment tested out so far?
Mars, for example.
And which spacecraft has been doing that so far?
One of the Mars rover, at least. I'm not as familiar with all of them, but the last Mars rover for one.
So we're in this awesome perspective where we have instruments. They have been tested as space ready, and we now just need.
Well, that's not quite where we're at because we have to send, like, if you can land on Mars, you can bring something more massive, and people do tend to like to make instruments complex with a lot of variables. If we want to go to Venus and do it quickly, we've got to streamline, and a streamlined instrument that we need is not completely ready yet.
And this is where we have to start looking at the fact that, like, Rocket Labs is looking to be one of the first companies to get something on its way to Venus,
Right.
and they have a, I believe it's 13-ish kilogram spacecraft that will allow, sorry, 15 kilogram spacecraft that will allow roughly 3 kilograms of instrumentation. And that's a
Not
lot.
sure what, yeah, I'm not sure what the exact numbers will turn out to be, but
Now, what all can you do that small that you're aware of?
well, we're working on it right now.
Okay.
Miniature instruments and such.
So, with all of this going on, there's a lot of questions that I, as a variable star astronomer by training, don't even know to ask. What I'm going to ask the most simplistic journalism question. What question do you wish a journalist would ask you that no one has asked so far?
Okay, well, I've talked to so many journalists and they've asked such great questions. Um, I mean, I could repeat some of the better questions, but I feel like I've been asked all the ones I've wanted to.
Okay, well that is a good thing. Um, with your team, what diversity of skills are you bringing together? You have observations, you have theory, you have folks that have the chemistry background and the biology background. We talk about astronomy being multidisciplinary, but we still mostly rely on people who are in astronomy departments or planetary science departments. Are you breaking down the boundaries as you do this and reaching in and being able to pull in people from other departments?
Not necessarily. We sort of usually take, we usually, we've been lucky to get students, at least at MIT, or postdocs who want to cross boundaries. And so, I do have a chemistry student, I have engineering students, but typically it's people who spend 3, 4, or 5 years even learning a skill outside or a discipline that's new to them.
And it's MIT is a really awesome place. I was lucky enough to spend a lot of years hanging out with the educational studies program while working at Harvard. And there is a creativity and a hacker spirit that is thriving at MIT that I haven't seen anywhere else, although I've heard that Caltech has it as well. Do you think that that hacker environment inspires the kind of creativity that's necessary to do this sort of work?
I do actually. And it's an enabling environment and culture as well, because in a lot of places it would be very frowned upon if you were to work on the search for life on Venus. But at MIT, there's almost no idea too crazy as long as it's actually doable. Not the finding or identifying life part per se, but finding a cheaper, faster, maybe better way to get to Venus. It's all supported.
And there is that everything is actually engineering uh, idea that goes into a lot of the culture that makes thinking about all of this more practical in some ways.
Right.
Um, so we're getting questions from the audience. Nancy Graziano is asking, what do you feel is the least publicized yet most significant aspect of the phosphine discovery?
Well, one of it's just the story, the behind the scenes story that I gave you the tiniest hint at, because I think, yeah, people don't usually realize, was this a purposeful search for life or was it kind of accidental somehow? The other thing is, I don't think people appreciate, like, it's hard to explain how many people hours went into this. So many. I think sometimes you feel, the criticism is like people don't seem to understand the depth that we've gone into with the chemistry or the data analysis. I mean, I'm sure that this is one of the more thorough things I've been involved with in my life. I mean, everyone tries to do their best and be as thorough as possible, but this one took it to a whole new level.
And this is one of those things that has got to be so frustrating for you, where there are a number of scientists who've done hot takes on this saying, well, there must be a geochemical way of explaining this. While you have Sosa Silver, I'm screwing up her last name, One of your colleagues goes by Dr. Phosphine on Twitter, and she has built her life on understanding this particular four atom molecule. Is it frustrating for you to know just entire life careers have gone into some of the
Well,
aspects of this research,
not
and then
really.
just
I
no?
mean,
Okay.
you've got to break it down a little, like what is a career? Is that 40 years, 50 years, 5
Yeah.
years, 10 years, So I think you've got to put things in perspective a little.
Um, so Paranor 001 is asking, could we have limited ourselves in researching abiogenesis only upon land? Could life start in the clouds and colonize any surface?
Good question, actually. We don't have an answer to that. It might be possible for life to form in the clouds. It's not something people usually embrace, though. They like the idea of life forming in a pool on the surface, where in a tiny pool where water could evaporate or a liquid could evaporate and ingredients can get concentrated. And then you can get more liquid and chemical reactions can happen and it can evaporate and get concentrated again and go over and over like that. It's harder to imagine that happening in a cloud environment.
One of the more interesting studies that's come out in the past couple of years is looking at how Venus may have been habitable up until as recently as 750 million years ago. And so there is that potential, given that here on Earth, 750 million years ago, we already had sponges, which are single cellular organisms capable of functioning in colonies. It's conceivable that on the same time scale, Venus could have been evolving life. When we think about life on Venus, do you think about processes that could have allowed that jump from the surface to the clouds? What are the pathways that you think about, not knowing which ones will prove out to be true?
Well, we haven't yet or aren't really able to delve into detail on that. We can say that on Earth, there's an aerial biosphere and life from our surface bacteria get swept up and they go into the atmosphere where they freely float or they get inside cloud droplets. And they only stay there for about a week or so before they're rained back down. So maybe it's not inconceivable to imagine that Venus life did that as well. And then it somehow found a way to get a foothold in the clouds and stay there for a long time. And that as Venus underwent its catastrophic runaway and the surface got hotter and hotter, too hot for life, that life on the surface died out, whereas life in the cloud managed to evolve and somehow survive and stay there.
Now, to switch gears entirely, our community has a citizen science focus. We were the community that worked with the OSIRIS-REx mission to count rocks and measure boulders on that rock pile of an asteroid Bennu. And many different people are asking how, if at all, could citizen scientists someday help with understanding Venus?
That's such a great question. And that question I haven't received yet. So yeah, I don't have an answer for that one right now.
Well, we're always willing to brainstorm with you.
Thanks a lot.
Looking to see if there's anything else in here. There's like a wall of citizen science questions. So Veronica Cure asks, how possible is it that this detection itself was an error? So, for instance, a different molecular line that overlaps, or because it was multiple telescopes and different sets of analysis, does that make it more likely that it is phosphine and not a different molecule?
Well, to the molecule question, and we were able to ask ourselves these same questions over the past 2 years.
Yeah.
So we did look at pretty much every possible molecule that could have an overlapping feature. And we didn't find anything really. We found one possible candidate, but it doesn't really exist in strong enough quantities to make a difference.
And just to back up for folks in the audience who aren't used to thinking about spectra, atoms and molecules, they have a variety of different energy levels that they can be at. With molecules, it's sometimes even just vibrational levels. And because a single kind of atom or molecule can have multiple different lines, we expect that if you see this line here, you'll see these lines in these other places. And this allows you to sometimes disentangle what could be multiple features at the same wavelength. Is that the kind of process that you guys implemented? Do you know?
Can you just repeat that last part a little bit, please?
Okay, were you actively looking to see, okay, these multiple different molecular lines can appear at the same wavelength, but because we didn't see lines at other wavelengths for this potential other molecule,
Right.
that is that the kind of
Yeah, we did that in one case where that was really, yes. But out at radio wavelengths, the rotational lines, like molecules rotate, and those
yes,
lines are typically spread very far apart. It's not like what you might be thinking at visible and near infrared. There's like a forest of lots of molecules that are overlapping, lots of lines that are overlapping, and it's just a big mess. Radio things are pretty spaced out. So, but there was a case where a line, one transition, one rotational line might overlap. Not really overlap, but be kind of near. And yes, if that line was present, we should have seen a much stronger feature of that same molecule, a different transition, which we didn't see.
awesome. Um, so looking to see if there's anything else. Um, so Larry asked, how does the isothermal nature of Venus's surface extend to the atmosphere? At the surface, the temperature is horrifying, from day to night and pole to pole. So what do you know are the temperature variations?
Well, the temperature variation is a lot smaller than you would expect. Even though Venus's rotation is so slow, it's effectively heated on one side and not heated on the other. There are very fast winds that move the atmosphere around, and heat gets trapped to the surface as well. So to my knowledge, the temperatures don't vary that much. It's kind of surprising, but yeah.
And those high speed winds, I'm glad that you brought them up. They have been one of the concerns for people planning either glider or balloon missions across the decades. How horrifying are these winds?
Well, the whole entire atmosphere moves around every 4 days. So they're pretty fast. But I think a balloon is fine. I mean, the Russians sent 2 balloons to Venus in the 1980s, and they just kind of go with the wind. They're not being shredded apart, if that's what you're thinking, but
Well, trying to steer, I'm thinking about more the how do you
yeah.
get from point A to point B while zipping along that fast?
I think in this case, they were just fixed altitude balloons, so they couldn't really maneuver.
Right. Um, so things to figure out as we look for things that can maneuver in the future. Um, so sorry, trying to track multiple screens. Um, Veronica Cura asks, what kind of life could create this element? So, um, the press releases simply say anaerobic life here on Earth is known to create phosphine. Um, is there any more detail you can go into beyond that for the kinds of life that could produce phosphine?
Well, on Earth, we don't know exactly which species is making it, but evidence points toward some kind of strain of E. coli.
Okay,
Yeah, some kind of E. coli.
that is convenient because that's one of the most well understood life forms. Um, does that mean that there's the potential for grad students to be creating Venus surrogate atmospheres in a lab and breeding strains of E. coli to survive?
That would be interesting, but the Venus atmosphere, unfortunately, it's just so different from our own. It has, instead of liquid droplets, the clouds are made of concentrated sulfuric acid droplets. So our life couldn't survive in it, and it wouldn't have time in a grad student's lifetime to evolve.
That is frustrating. I know some life, for instance, they will specifically breed out the bacteria for different sewage treatment plants, evolving it rapidly to the needs of a given city. But I guess for a graduate student, you don't want to take that risk where you have 4 to 6 years for something to happen. Um, and of course, there are the standard Montezuma's revenge comments now being made about it being E. coli. What what impact would this have on the potential size of the life forms? We know things as complicated as tardigrades are capable of completely desiccating themselves out. Is there an upper limit on how big a life form could be at the still small level?
In the Venus atmosphere, you mean?
Yeah.
Or yeah, we're really not there yet. I mean, we really just focused on phosphine and how it might be produced abiotically. We didn't start working on life or what life could be like.
Okay. These are early days, and unfortunately questions leapfrog ahead of
Yeah, and some of the questions, they're really easy to ask, but they're, you would say, nearly impossible to answer.
Yeah, I mean, at a certain level, you have to hope that looking at high deserts allows us to get a sense of desiccated life, but life always finds a more creative way to do things than we thought of. So we can only get hints at what's out there. Um, so Raj Luthra asks, if there's microbial life on Venus, does that mean there could be microbial life on other extraordinarily hot worlds? Do you have a limit from your research on how hot a world is capable of supporting this kind of a life cycle?
Well, as long, this idea does certainly open up the possibility that hot worlds could have life as long as that life exists in the clouds. So yes, we don't have like a number to give you, but as long as that atmosphere is cool enough, it should be fine.
So something like Kelt 9b, Kelt 9b, which is hotter than the surface of the sun at its surface, probably won't have any life even with this.
No, because there are certain laws of physics,
Yeah.
that you can work out for a given atmosphere about how much it cools above the surface or above the atmosphere, or, so you make a measurement of a temperature and then you can figure out the range of temperature within the atmosphere. That one's way too hot.
So we still need to have something, I'm guessing below boiling somewhere in its atmosphere.
Probably, yeah. That was a much better way to say it. Thank you.
Okay. All good. So Heisenberg 2020 says, um, I'm designing a satellite mission to Europa. When I tried to design the thermal subsystem, I find all textbooks, so this is a school project, keep the sun's radiation constant at P equals J alpha A. I'm not familiar with that relationship. The relationship has nothing to do with the distance of the satellite from the sun. Is that true?
So I can't, there's not enough info for me there.
Yeah, I'm sorry, Heisenberg. Try dropping me an email or DM me on Discord, and I'll see what I can do to help. So Sir Giddy, that is completely unrelated science. So we're trying to stay close to the sun this time. So this is the kind of thing that is going to, of course, lead to myriad science fiction, I'm sure, happening. Are you a science fiction fan at all?
Like, more, I am. I'm not a huge science fiction fan buff, but I do really like it.
And
One of my students told me there was an episode of The Expanse. Do you know what that is?
yes, yes.
And she told me that they went to Venus, like people went there and stayed in the atmosphere in some kind of structures.
And you actually bring up an interesting comment that someone made during the press conference. One of the aspects of the Expanse series is there's this protomolecule that essentially zombifies life. I'm not sure of how better to put it. And the joke was that you found the protomolecule in Venus's atmosphere, which was a rather dark take on things.
Interesting.
So with Venus, prior to the Mariner 2 observations, there was this it must be habitable, amazing science fiction, all looking at life now on Venus. And then Mariner 2 results came in and science fiction stopped that. With this science changing, looking at a potential habitable past, looking at maybe microbial life in the atmosphere today, what kind of science fiction topics are you hoping someone decides to write?
I mean, it may be fun to have more on Venus. I don't know if it's all been exhausted yet. You probably know more than I do.
Okay. Um, there's no one thing where you're like, write this story for me.
No.
Okay. Um, so we're starting to run down on the end of the hour, and I know both of us have meetings starting at the top of the hour that we need to get to. Before we end this interview, is there anything in particular that you want to leave people thinking about in relationship to astrobiology and perhaps this discovery in particular, or astrobiology in general?
I just want to say that our planet, our solar system, our galaxy, our universe is full of surprises. And we should never let, mainstream thinking limit what we try to find.
We should never stop being creative.
Yes.
I think that is awesome. So thank you so much for being here.
Thanks for having me.
I hope you're able to find time to pursue all the research you must be dying to do in the midst of all of this media chaos during a semester. I can only imagine how crazy your days are right now. Thank you. Thank you for being here. And thank you for being here, audience. This concludes our daily space for today.